Good afternoon, everyone. My name is Elena Жарких. The topic of my presentation have been already mentioned, so let's move with the presentation. Sorry. Okay. As all of you know, for many methods of biomedical photonics, the microcirculatory tissue system is one of the main objects of the study. And the microcirculatory bed is a complexly organized system that exchanges between blood and tissues necessary for ensure cellular metabolism and removal of metabolic products. And consequently, this microcirculatory system is the first link that involved in the pathological processes in the many extreme situations. For example, circulatory disorders appears in such common diseases as diabetes mellitus, hypertension, or coronavirus disease. Thus, high social, economic, and social damages from these conditions determine the necessity to development of mobile monitoring of health parameters and early diagnostics of the blood flow disorders. Laser Doppler flowmetry is one of the main of most popular non-invasive methods for blood flow perfusion monitoring. And this method was first introduced more than 30 years ago and has undergone consistent development since. In laser Doppler flowmetry, coherent light directed toward the tissues is scattered by moving objects and by static tissue structures as the photon migrates through tissue in a random pattern. When scattered on the moving project, which is predominantly red blood cells, this light undergoes frequency shift according to the Doppler principle, and light scattered from the static tissues remains unchanged in frequency. So when we detect on the photodetector the light coming from tissue, the resulted signal is proportional to the amount of the red blood cells in the probing tissues and their velocity distribution. Devices which implement laser Doppler flowmetry methods usually use single mode fiber coupled infrared laser as and one of several photodetectors with appropriate signal processing. And here you can see some examples of the devices which utilize this method. Another method of biomedical photonics which has found wide application in many areas of medical studies is fluorescence spectroscopy. This method is based on the excitation of the fluorescence of endogenous and exogenous fluorophores of the biotissues and recording the radiation in the visible regional spectrum. And this method is highly sensitive and allows for non-invasive tissue oxygen metabolism diagnosis. So due to the high requirements for radiation sources for the laser Doppler flowmetry channel, there has been little research to date on miniaturized and possible development of wearable diagnostic devices which implement this method. But recently, a significant breakthrough has been made in this area with the development of wearable devices which implement laser Doppler flowmetry and fluorescence spectroscopy channels. You can see the example of these devices on the slide. These devices has already been established in the several applications in medical practice, particularly in the diagnosis of the complications of the microcirculation in diabetes mellitus, hypertension, coronavirus disease, and so on. But there is still more research to be done to improve our understanding how the devices work. So the aim of the study was to investigate the peculiarities of the propagation of optical radiation in the laser Doppler flowmetry and fluorescence spectroscopy channel of these wearable diagnostic devices in biological tissues based on the Monte Carlo simulation. So the present study used Monte Carlo simulation of optical radiation propagation in the biological tissues. And the Monte Carlo method provides a precise solution of the problem of light transport in complex turbid media with a complex structure, which has made it a popular tool for modeling of light propagation in biological tissues. And in the generalized model of the Monte Carlo simulation procedure is presented here on the slide. In this generalized model, light transport in tissue is modeled by tracking the random steps which photon packet undergoes while it moves in the tissue model. For this work, two approaches for Monte Carlo modeling were used, and for laser Doppler flowmetry channel, an inline object-oriented Monte Carlo computational tool was used to analyze the probing volume. And for fluorescence spectroscopy method to model the propagation of optical radiation, trace pro software was used. So in the present work, we simulated the optical radiation propagation in the model of the human skin, represented as a three-dimensional semi-infinite model medium divided into several layers with different optical properties. And this simulation was done for two areas of interest, namely it was made for two types of skin, non-glabrous or hairy skin and glabrous skin. Glabrous skin covers palms and soles of the feet, and non-glabrous skin covers almost most surface of the body. And these skin types have several functional and structural differences. And the main structural difference which was taken into account in this simulation was the greater thickness of the epidermal layer in a glabrous skin, which is due to the presence of the additional cells layer in this type of skin. This slide shows the parameters of laser Doppler flowmetry channel taken into account while modeling. Laser Doppler flowmetry channel in the studied devices is implemented with optical radiation of 850 nanometers. And in the table, you can see the parameters, optical characteristics of the skin for these wavelengths taken from the literature review. And on the right part, I don't know if you can see it, probably. Okay, and the right part, you can see the geometry of the emitting and recording parts of the probe. So in this part of the study, 1 million photons were used to simulate the probing volume in the laser Doppler flowmetry channel. And here you can see the results obtained for this channel. And for glabrous and non-glabrous skin, you can see that from the simulation results that the depth of the probing for this channel reaches 1.5 millimeters. There is no much difference between two types of skin for this channel. Probe tissue volume reaches reticular dermis, and the value of diagnostic volume for this channel is about 3 to 4 cubic millimeters. Here you can see the parameters of the fluorescence spectroscopy channel taken into account while modeling, and the fluorescence spectroscopy channel operates on the wavelengths of 365 nanometers in these devices. The table shows the optical characteristics of the skin for this particular wavelengths. And here you can see the probe geometry with the geometry of receiving and transmitting parts. The simulation was performed in trace pro software environment. So in this part of the study, the motion of only 200,000 photons was simulated, which is due to the limitations of the software. Here you can see the results of the distribution of fluorescence rate in the two types of skin. And as you can see, the probe tissue volume reaches almost 30% of the reticular dermis for non-glabrous skin, and 70% of the reticular dermis for non-glabrous skin. For our assumption is this cause this layer, this is because the higher thickness of the epidermal layer. In this case, because this epidermal layer contains more fluorophores, which is taken into account. So to conclude, the simulations showed that in laser Doppler flowmetry channel for both types of skin, the probe tissue volume reaches reticular dermis, and the diagnostic volume is about 3 to 4 cubic millimeters. And for fluorescence spectroscopy channels, the diagnostic volume is about 1.5 millimeter for non-glabrous skin and 4.5 millimeters for glabrous skin. The obtained result can be used to better understand and improve the quality of diagnostic information which we obtain with wearable laser Doppler flowmetry and fluorescence spectroscopy monitors. And this result will be used for substantiate the specialized medical technical requirements for wearable multimodal diagnostic devices. Thank you for your attention.